But what happens if you have an equilibrium that's established and then you disturb it? You mess with it. It's like the neighborhood's all peaceful, and then somebody comes through with their big old stereo and is blasting whatever, screamer music or something. It disturbs the equilibrium, right? What do the neighbors do? They're going to come out and shake their fist at you. They're going to call the police. They're going to react, right? Something's going to happen. They're not just going to take it. Unless you've got super, super peaceful neighbors. In a chemical equilibrium, the system will fight back as well. And this is called Le Châtelier's principle. When a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. In other words, it fights back when disturbed. How can an equilibrium be disturbed? Well, if you throw a bunch of reactant in there, it's going to be disturbed. Or if you throw a bunch of product in, or if you steal the product out of there, you're disturbing the equilibrium. You're changing the concentrations, you're disturbing the equilibrium, and it's going to fight back. So back to the Narnia Middle-earth analogy. So we had this equilibrium established where there were a few people moving back and forth, but we had constant numbers of people in each kingdom. And now, I don't know where these people are coming from. I think they're coming in a spaceship from Mars. And they're coming and they're landing in Middle-earth, and now there's a whole bunch more people over here. What's going to happen to the migration of people? We've increased the concentration of people over here. What does that do to the rate of people leaving Middle-earth? It's going to increase it, right? Increasing the rate of people leaving Middle-earth is going to help undo what was done. So a whole bunch of people were dropped into Middle-earth, and the system reacts in a way to undo that or fight back. Like, oh, you've put a bunch more people in here. Well, we're just going to move over here and partially undo that. Now, you can't completely undo it, because if you put too many people over here, then you'll have more crowding over there, and it'll go back and forth. And eventually, though, it's going to settle out and be at equilibrium again. What if you took like 2/3 of these people and, sorry, this is politically incorrect, but what if 2/3 of these people died from the Ebola virus? Right? And then there was a waiting period until we were sure that everything was decontaminated, right? What would happen to the population? How would it shift? It would shift over here because there's a whole bunch of people gone, fewer people, more people over here. The rate of the forward reaction would be greater than the rate of the reverse reaction, and so it would shift. So if you add people to one side, the reaction shifts to the other side. If you take people away from one side, it'll shift towards that side, trying to replace them. So the reaction is fighting back against the changes being imposed on it. So here's a reaction again, N2O4 in equilibrium with 2NO2. If we add a bunch of NO2, the reaction is going to shift to the left, meaning we're going to have an increased rate of reverse reaction, and the amount of N2O4 is going to go up, trying to reduce what was added. Does that make sense? This is one of those things where you just kind of have to be able to think about it and understand it rather than just rote memorization of an equation or something. So here's pictures, because pictures are good. So here we have an equilibrium, and we're going to add a bunch of NO2. So here's the NO2 being added. The reverse reaction is when two NO2 molecules collide and form one N2O4. If we've got more of these, the reverse reaction rate is going to go up, and we're going to get more reactant formed. And as more reactant forms, the rate of the forward reaction will go up a little bit, and they'll change until they come to the same rate again. And now we have a new equilibrium established. Here we had 2 N2O4 particles, and now we're going to have, I'm assuming these guys are getting together, we're going to have 3 N2O4 particles. The concentration of products is higher as well, but it caused the reaction to shift. We don't see these come in and just sit there and do nothing. They affect the equilibrium. If we add N2O4, it causes the reaction to shift to the right, to undo what we've done to it. It's fighting back. So here, adding reactant will cause more of the forward reaction to occur, and we'll get an increase in product. If a chemical system's at equilibrium, increasing the concentration of one of the reactants causes the reaction to shift to the products. If you increase the concentration of a product, it causes the reaction to shift to the reactants. So let's look at this equation and see what happens when we add Br2. If we add Br2 to this, is the reaction going to shift to the right or to the left? It's going to shift to the left, because when we add Br2, it's going to go to the left, trying to get rid of some of that. What if we add BrNO? Right or left? It'll shift to the right. So we're adding to this side, and it's going to shift the other way, trying to balance things out. What if we take away some bromine? It'll go to the right because it's trying to replace it. Does that make sense? Oh, you took some bromine away? Well, I'm going to shift, I'm going to make more. I like things the way they are. I can relate to this because I only like change if it's my idea. I don't like it when other people impose change upon me. So if we remove some Br2, it'll shift to the right. So those are the kinds of questions we're going to ask you on an exam about Le Châtelier's principle. If I change this, does the reaction shift to the right or to the left? Any questions?